Okay, so now we're going to talk about another alternative energy. I'm not sure I would call it a renewable energy, but it is the splitting, which is called fission, of the nuclei of atoms to produce energy. The cost of nuclear fuel is cheaper or competitive with fossil. It produces no air pollutants. However, here's the big problem. It produces fuel that is used fuel is highly radioactive, and we ain't got no long-term storage in this country. We've been trying to get one for decades, and is still not ready. Called Yucca Mountain in the Yucca Mountains. There are 103 existing reactors, and they are storing their stuff at their area. And that lovely waste stays dangerous for thousands of years. See these little guys, these little pellets? These are quite lovely little pellets. See how small they are? And one of those pellets, it's about a racer size. She is going to be equivalent to about 50 barrels of oil or a ton of coal in energy. How does it work? Nuclear fission is, like I say, the spinning of large nuclei into smaller ones with the release of a super load of energy. So here we go. We're breaking the laws of conservation of matter and conservation of energy, because the energy is released because the sum of the masses of these fragments is less than the original mass. So we have, let's start with like uranium-238. There she is. You hit her with a neutron, and she's temporarily heavier by one neutron. And then, remember, this guy is the atomic number, this is the mass number. And she splits her nucleus. In this case, they call them daughters. In this case, I've written barium, and krypton is another good one. And what the big deal is she also produces that which started it. So it is a spontaneous chain reaction. They do keep it very controlled in a nuclear reactor, unlike in a nuclear bomb, where you have to have this critical mass. And if you've got that, then it spontaneously reacts in a very short period of time. The missing mass, about 0.1% of the original mass, has been converted into energy using, ta-da, our friend Einstein's famous E equals mc squared equation. E is energy, not Einstein, energy, and this is like the change in mass, the difference in the mass of the daughters from the parent. And the deal is you have to use mass numbers or molecular weights to I don't know, 8 significant figures in order to see this change in mass. And here we go. This is the big deal. This is the speed of light, and her magnitude is 10 to the 8th. So if you square her, she's 10 to the 16th. Oh my gosh. So if you take 1 kilogram of isotopically pure uranium-235, which is really hard to do, actually. If you look at the atomic weight for uranium, it is 238.00 something. That means that most of the isotopes are this 238, which is much more stable. It is the 235 isotope that must be used. This is very hard to purify. This is why so few countries have nuclear reactors. If you've seen the pictures of Iran and their cyclotrons, that is what is purifying. They turn it into a compound, and the compounds weigh slightly different, and when they subject them to spherical force, they have different responses based upon mass. Very small difference in mass. Okay, so E is, the difference will be 1 gram out of that 1 kilogram. That's the 0.1%, times 3 times 10 to the 8th. Here is the C right here squared. This is how much we get. Holy camoli, 10 to the 13th joules. If you want to think of dietary calories as 10 to the 10th calories, which is equivalent to 6 million pounds of coal, 7 million pounds of TNT, 20 million megawatts of power. Or as our textbook likes to say, 1 gram's enough to propel 750,000 cars 6 miles high. Oh yeah. All right, so what do we use it for? Well, we use it to boil water, just like in using coal. They use the heat of this reaction The energy comes off as heat, that energy that we just saw, and it's used to change liquid water into steam. And then the steam does the same thing. It turns the paddles of the turbine, put it through a generator, and it makes our electricity. Then you take it down, you cool it down again. And this cooling area, ooh, the manatees love it. It's so warm. It's called thermal pollution. The fish aren't too hot about it because the warmer the water, the less oxygen it holds. But the manatees, being mammals, they love it. A nuclear reactor is a device. So you've got a nuclear chain reaction, but they're very controlled. They put, for example, neutron getters in there so they can control how many neutrons are bumping around. And they want it to be a steady rate. They do not have a nuclear explosion. That is not possible because they don't have the material together, the critical mass together at any one time. This image shows the fuels. Oh, they glow beautifully. What they're doing is they are energizing the molecules around them to put off light. That's so much energy coming off. Okay, 2 cooling towers. This is just steam. This is not radioactive material. Okay. And who uses it for electricity? Remember, it's electricity. It's not like you've got nuclear-powered cars. We got some up here for node. Overall, the U.S. has about 20% of their electricity from nuclear, so this is percentage. France is the king. France is 76, and they re-enrich their fuel so they can reuse the spent stuff. Therein lies all the difference. We are trying to get one here, a Piketon plant to enrich uranium. But Western lawmakers were worried that putting more enriched uranium on the market could hurt the market price for uranium. Oh my gosh, it's always something, isn't it? And they'll have an impact on the domestic mining industry. But they are looking for a $2 billion loan to start this Piketon enrichment plant. And as you know, they talk about jobs, they talk about money to the local economy. And that would be great. We shall see what happens. They're also looking for a cracker plant to break down large molecules of oil and gas into make more gasoline. So this gives you an idea of how much energy is part of our economy in terms of jobs as well. So what is radioactivity? It is the spontaneous emission of radiation, either directly from unstable. This is just, let's just remember that. And radiation has different forms. I just want you to be aware of the different forms. I'm not going to test you on them. But, for example, alpha particles, these guys are like the helium nucleus, meaning that he has 2 protons and 2 neutrons in him, no electrons. A beta is an electron, and a gamma is a photon. Photon is like a packet of light. It doesn't have mass to it. It's just radiation energy coming off. And when you decay, for example, you bing, 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 all over the place, making little babies with different atomic numbers, and there is a repeatable pathway that they do. And that's all I got to say about that. You're not going to be charged or asked about that. Okay, let's talk about some of the problems that we've seen. Here's Chernobyl. Chernobyl is still a no man's land. It was a chemical reaction, ironically during some safety tests, I believe. And it is a chemical explosion. So this is like a dirty bomb. It was not a nuclear meltdown. It was a big explosion. I think the carbon rods caught on fire. You know it's got to be hot. And it spewed this crap all over its neighbors. And this was a Soviet Union, and they tried to keep it quiet, which made it even worse, so people could not prepare for what was coming. 3 Mile Island, as she was a minor meltdown, but all the safety provisions held. So about 2 million people were exposed. But very little to Low, low dosage. They say the guy at the front gate had about as much radiation as getting a chest x-ray. So, but people also said, maybe I'll take one of those lows away, because they said all the way in Hershey, they tasted metal, which is not normal. You're supposed to taste chocolate in Hershey. Okay. Now, we have Fukushima, which was the result of a tsunami coming from an earthquake. The one in Haiti was 7. This guy is 9. These are logarithmic magnitudes, so this is 100 times worse or more turbulent. And it's going to take them untold fortune and decades to clean this up. And it's very scary. We got 80,000 people, and it's amazing how many of these plants are right on the water, even in the United States. So here we are in March in the 2012, and they still favor, even right after Fukushima, they still see it as very safe. It is much different between men and women, though. That's kind of strange. But it is an acceptable form. You cannot have it is extremely, like I say, difficult to separate them. That's what the centrifuges is. And building deploying nuclear weapon is a very difficult operation to carry out. How about very, very, very? And my problem is the nuclear waste. You're not going to have a nuclear explosion at a electrical plant, but you have to worry about these spent fuel rods. They encapsulate them in glass. They call it vitrification. Store them in casks, and they are on site. They're hoping to send them up to this yucca. And they've already spent, yeah, that's B, $10 billion, and they keep starting over again. And this is a huge amount of cost, which is not taken into consideration when they say, oh, it's so cheap. It is tens of millions of dollars every year. The government pays the nuclear power plant operators to store the waste themselves. I don't know why. Okay. All right, I love this. This is, they took out of the book, but I had to keep it. Look at this guy. This is the year 12,000. I'm sorry, this is the year 12,000. And this is the end of the regulatory period of 10,000 years. I do not think the government's going to be the same as it is today. And they are hoping that the waste packages, they found something better to do with them because they're figuring they're going to fail dead. Okay?